All right, here is the video for the activity solutions in section 4.1. So I've asked you here to again look at the area between x squared and the x-axis on 0 to 3, but unlike the introduction, I asked you to find the right sum, left sum, and midpoint sum with 6 subintervals. So this changes the game ever so slightly in the sense that delta x, or the width of our intervals, is now 1/2. The total interval width is 3 minus 0, and the number of subintervals is 6. So that gives us the width of each interval as 1/2. So we see here, if we zoom in here on the drawing of R6, we see that we're interested in the heights of our rectangles at 1/2, 1, 3/2, 2, 3/2, and again at 3. And so we're going to need to know the output of the function at each of those spots to find the heights of those rectangles. So that makes R6 the width, delta x, this is width. And then the height of that first rectangle is the output of the function at 1/2, f of 1/2. So that first rectangle looks like 1/2 times 1/2 squared, that is 1/4. The second rectangle has width 1/2 times height 1 squared, which is 1, width 1/2 times height 3/2 squared, which is 9/4. And we keep going along to get all 6 of those rectangles, and we get 11 and 3/8 square units. I don't know what the units are here, so we'll just measure them as square units. Okay, we do something similar for L6, except if we zoom in, we see that the heights of the rectangles are now the left-hand endpoint. So the first one is the function at 0, then the output of the function at 1/2, 1, 3/2, 2, and finally at 5/2. Those are giving us the heights of our rectangles. So here we go. I know that each rectangle has the same width, so I factored that out to start to make my life a little bit easier. And then I know that I need, for each of the heights, I need the output of the function at 0, 1/2, 1, 3/2, 2, and 5/2. And so I square each of those things to get the respective heights of my rectangles. I get 0, 1/4, 1, 9/4, 4, and 25/4, and I should get 6 and 7/8 square units. Okay. Zoom in now on M6, and the heights of those rectangles were all drawn from the midpoints of the intervals. So those are how we drew the heights of our rectangles. And so the heights of all of those rectangles are going to be the output of the function at each of these values: 1/4, 3/4, 5/4, 7/4, 9/4, and 11/4. Similar to L6 here, I knew the width of each rectangle. Here's delta x. I know I need the output of the function to get the 6 heights. Square all of those things because that's what my function is. And I get 8 and 15/16 square units. And you'll see in the beginning of the next section that's a pretty good estimate that we get here with M6 in this case. Okay, all that was left here was the challenge. All that was left, it's a challenge. But it's a process we're going to have to go through here to help find these areas. So let's find the right-hand sub with n subintervals, Rn, for the area between f of x equals x squared and the x-axis on 0, 3. Looks like we're missing a parenthesis here. Sorry about that. All right, so I've drawn the function. We're looking from 0 to 3. We looked at this in the introduction. The width of each subinterval is going to be 3 over n. So again, I took out the x-axis and I labeled the points here where I am going to, the points which are the endpoints of my subintervals. 0, we move over here, a width of delta x. We move over another delta x, another delta x, another delta x. And there's a delta x in here also. There's another delta x here. I can't draw them all in. This dot, dot, dot is here because I don't know what n is, right? So I just have to see what the pattern is that's happening with these subintervals. So they all have width 3 over n, and they all have height, the output of the function at the right-hand endpoint. So the first output of the function, if we zoom in here, is 3 over n squared. The second output of the function at the right-hand endpoint is 6 over n squared. So what does that make? Let's see. So if we just look on that interval from 0 to 3 over n, the area is 3 over n times the output of the function, which is 3 over n squared. On that next interval, from 3 over n to 6 over n, the area is 3 over n times 6 over n squared. Okay, and we just keep playing that game. We go to 9 over n and we end up at the end, right? We're going to have a rectangle here where we're going to need to know the output of the function at 3 over n times n minus 1, and we're going to have a rectangle here where we need to know the output of the function at 3 over n times n. And so we add all of those things up, and now we can do some algebra. We can factor 3 over n out of each of those terms. Again, this dot, 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 I don't know n. So I see some pattern. Each of these things that's being squared is increasing by 3 over n until I eventually get to the last n point, because that's the last right-hand rectangle that gets drawn. Then let's see, I can square those things. I get 9 over n squared plus 36 over n squared plus 81 over n squared all the way across. I know I could have simplified this one as 3, but it's a little easier to see the pattern that's happening here if we leave it as 3n over n. Now each of those terms has a 9 over n squared in common, so I can factor that out. And when I factor that out of each of those terms, I get 1 plus 4 plus 9, dot, 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 up to n minus 1 squared up to n squared. That 9 over n squared I can factor out in front, and I get 27 over n cubed times that sum. Okay, so this is a good time to take a slight aside here, because we're going to need some notation. So here's a notational aside. Here's another way to notate this. This is the sum from I equals 1 to n of I squared. Okay, we're going to need this summation notation. What does this summation notation say? It says start with I being 1, put that in here, and do whatever you're told to do to I. That's square it. Then add to it. Now bump this index up from 1 to 2, square it. Bump that index up from 2 to 3, square it. Bump the index up to 4, square it. Keep going until you get to n. Stop here. N squared. All right. So one more aside, just to try to get this notation down. If it was the sum from I equals 1 to 3 of 2i minus 4, what would that look like? Well, it would be 2 times 1 minus 4, that would be our first term, plus, now we bump the sum up to the index up to 2, 2 times 2 minus 4, that'll be our second term. Now we bump the index up to 3, 2 times 3 minus 4. But 3 is the upper limit of our sum here, so it's the last index. We'd only have 3 terms. And it looks like we would have negative 2 plus 0 plus 2, and in fact, this sum would end up being 0. That was a coincidence. That wasn't intentional. Similarly, if I had the sum, let's go the other direction now. What would this sum be? The sum from I equals 1 to n of I. What does that look like? Well, start I at 1. That's 1. Bump it up to 2. You don't do anything to it. Bump it up to 3. You don't do anything to it. Bump it up to 4. And keep playing this game until you get to n. Okay, so that's how this summation notation works. Move our index up 1 step every time until we get to the top step on the ladder there with our notation. So you'll see a couple problems in the book, and this notation will come up a little bit as we are finding these areas moving forward. Okay, so see if you can take this and tackle the homework for section 4.1.